the next example we're going to do is with H2O. So the first step in this procedure is to write the Lewis structure for H2O. So I'm going to do the math very shorthand. Remember, if you want to do the long version of the math, you are more than welcome. So what I'm going to do is I'm going to look at H, hydrogen. That is in column 1A, so it's going to have 1 valence electron, but 1 times 2 is 2. And then oxygen is in 6A, so it's going to have 6 for a total of 8. And as far as probable, each hydrogen is probable to have 2 electrons, times 2 is 4, plus 8 for oxygen is going to give me 12. 12 minus 8 is 4, divided by 2 is going to give me 2 bonds. So when I draw this structure, I'm going to put oxygen in the middle, and then to combine 2 hydrogens with 2 bonds, I'm just going to do single bonds. If I count my valence, that's 2, 4, so then I need 6 and 8. Remember, hydrogen has a special octet rule, they only need 2, so that's why those electrons are automatically going to go on the oxygen. I'm going to go ahead and erase this math real quick just so I have some more room here. So the next thing we have to look at is going to be the electron geometry. Remember, the electron geometry has a lot to do with, or all to do with, the number of domains. A domain is anything that is attached to the central atom. So if I use my highlighter and I count, there is 1 bond here, 1 pair is 2, 3, 4. There are 4 domains. A bond and a pair of electrons count as a domain. So for this particular molecule, the number of domains is 4. So then what I'm going to do is bring up my first chart. You can see here. It's right in your packet. And I'm going to find the number of domains. We just found 4. And I'm going to look to see the electron geometry is something called tetrahedral. So I'm going to go ahead and write that in the box. So all I did was I drew my Lewis structure. I checked to make sure it was correct. I counted the number of things attached to the central atom. It's very important that you only count the one in the middle. I found that it had 4 domains. I used this first table to figure out that electron geometry would be tetrahedral. If you notice in this chart, I can also find the bond angles here in 109.5 because that also has to do solely with the number of domains. So that's using the first chart. The next thing I'm going to do is look at hybridization, which has to do with the third chart here. So again, I'm going to go ahead and look and find that I'm going to need 4 domains, which is right here. And if I look down, the hybridization should be sp3. Notice you can also find the bond angles and actually the electron geometry with this table, with table number 3. So those are pretty easy, those couple of things. Basically, you just need the number of domains, which is easy to find. Remember, it's the number of things attached to the central atom. The third thing, the last thing, molecular geometry, is a little bit more difficult. Molecular geometry is not only the number of domains, it is also the number of lone electrons. So the key of molecular geometry is these 2 right here. These lone pairs of electrons push away the bonds more so than just regular bonds. So it's really going to affect the shape of the molecule. So what I do to find the molecular geometry is I use table 2. I'm going to find 2 things, the number of domains, which is 4, and then also the number of lone pairs. So if I look in this picture, I have 2. And then you just find where those 2 numbers intersect, and I see that my molecular geometry, the way the molecules are really arranged, is in a bent structure. Because of that, because the molecular geometry and the electron geometry are not the same, I have to edit my picture because I drew my picture assuming that the electron geometry is not correct, and it's not. So I have to erase my picture. That's why we're using a pencil. The basic is still the same. Oxygen is still in the middle. But the bent structure tells us that because it has 2 sets of valence electrons at the top, like Mickey Mouse ears, that the hydrogen bend away. The shape of the bonds for the hydrogen is pointing away from those lone pairs of electrons. So I had to go back and fix that. If the electron geometry and the molecular geometry are the same, if the word for those two things, the description of their shape is the same, then you don't have to change your structure. You only change your structure when the molecular geometry says that because of the lone pairs, the bonds move.